மேம் நான் பேசுறது மட்டும் கேக்குதான்னு பாருங்க. அன்மியூட் பண்ணேன். அது ஹெட்ஃபோன்ஸ் நார்மல் ஹெட்ஃபோன்ஸ் வச்சிருக்கேன். ஹெட்ஃபோன் எங்க வச்சுன்னு தெரியல. மியூட் பண்ணீங்க. Okay. Ma'am.
பண்ணலாமா? ஹலோ மேம். ஹலோ ஹலோ மேம். Ma'am, whether my voice is audible, ma'am?
Hello.
Ma'am, audible இருக்கா? Hello.
Hello.
Ma'am. Ma'am.
Hello. Hello.
Hello, நீங்க பேசுறது
Hello.
கேக்குதா? Whether my voice is
Hello.
audible? Hello.
Hello. Ma'am, am I audible? Am I audible? Okay, thank you. Dear participants, kindly wait for some more minutes. The session will start around 11 o'clock. Madam, phone la pesla.
Hello, ma'am.
Hello.
Hello.
Dr. Nalini,
Ma'am,
ma'am.
whether my voice is, yes, ma'am. Am I audible, ma'am? Myself from Nalini, whether my voice is audible?
Dr. Nalini, ma'am.
Yes, ma'am. Yes, ma'am.
நான் பேசுறது கேக்குதா?
Hello. Participants, are you able to hear my voice? Just any of you kindly message in the chat. Thank you so much.
Nalini, ma'am.
Yes, ma'am.
Am I audible to you, ma'am? I'm Dr.
Yes,
Megla,
ma'am.
ma'am.
Yes. Yes, ma'am. Yes, ma'am. Your voice is audible,
Good
ma'am.
morning, ma'am. Thank you, ma'am. Good morning.
Good morning. Good morning.
Ma'am, let us start the session by 11, ma'am.
Okay,
We'll wait
sure,
for
ma'am.
some time. Thank you, ma'am.
Sure, ma'am.
A very good morning to all. Am I audible? Yes. Thank you so much. First of all, I'm Dr. T. Megla, a coordinator for today's FDP on machine learning and its real-time application. And a very warm welcome to all the participants who have joined us for the today's FTP. And it's my great privilege to welcome Dr. Nalini, Associate Professor, Department of Information Technology, Rajalakshmi Engineering College, for as a today's speaker. And I'll hand over the session to Mrs. S. Deepa, Assistant Professor, Department of Computer Science and Engineering, to deliver a welcome address. Okay. Mute பண்ணு. Am I audible? Am I audible? Yeah. Okay. Thank you, ma'am. Good morning to each one of you present today. It's a moment of extreme pleasure to welcome the participants who are present here to attend this FPP. On behalf of Sri Manakala Vinayakar Engineering College, I welcome our resource person, Dr. S. Nalini, Associate Professor, Department of Information Technology, Rajalakshmi Engineering College, Chennai. She has received her PhD and MA from Satyabama University. She previously she has worked HOD in the Department of Information Technology at JPR Momalan Engineering College. She is having 18 years of teaching experience. She is XTIZ alumni of IIT Madras, NVIDIA certifier of deep learning for computer vision and multiple data types. She has published 15 national and international journal papers, 10 national and international conference papers, books and patents, etc. Her area of interest includes cloud computing, blockchain technology, AR, VR, data science, and machine learning. Welcome you, ma'am. Once again, I welcome all the professors connected for this FTP. Thank you. I'll hand over the session to Dr. Nalini, ma'am. Ma'am?
Yes, madam.
Okay, ma'am. You can continue,
Okay.
ma'am.
Okay, thank you.
Thank you.
A very good morning, a pleasant morning to all the participants of today's session. Let me first of all thank the management of Dr. Sri Manakula Vinayakar Engineering College, and special thanks to Mrs. Deepa ma'am for inviting me as one of the speakers in day 2 of the 5 days FDP. So let us now dive into the topic of discussion today. Let me share my screen. Whether my screen is visible?
Yes, ma'am.
Okay.
Sure.
Okay. So without further delay, let me just share whatever views I'm having in the topic clustering techniques. So as we all aware that clustering techniques, the agenda of today's discussion will be like this: introduction of clustering techniques, mathematics behind clustering, and then the techniques that is available and references. So moving on to the introduction part of clustering. So we know that cluster actually is group of items. So we will prefer to have this particular unsupervised machine learning technique called clustering to group similar items and to create a cluster. Actually, if you have a complex or huge amount of data, to simplify them, to gain insights into the data, we have to prefer to use clustering. And since I was telling you, and we are all aware that comes under unsupervised machine learning concept, our data actually will be like labeling will not be that they are unlabeled data set. In that case, we used to prefer this unsupervised machine learning, which is our clustering. So before actually start or beginning with clustering, we should know how to create cluster. So generally, we will be categorizing them based upon their similarities. Okay, so homogeneity. So we will be creating homogeneous groups from heterogeneous observations. And this particular clustering, we are all aware that it depends upon the distance-based algorithm. Everything, it is based upon the distance calculation. So the aim or the target of clustering is to minimize the intra-cluster distance, maximize the inter-cluster distance. So just to picturize you, unclustered data will be like this. After clustering, similar items will be grouped and we'll be visualizing like this. So the mathematics behind clustering, we have to group the items based upon the similarity. So before clustering, we need to find what is the similarity between the items that is present over there. So measuring the similarity between the items, we need to use some of the distance metrics to measure the similarity between the points or the data items that is present over there. So to measure that, we'll be having the commonly used distance metrics in machine learning is Euclidean distance, Manhattan distance, Minkowski distance, and Hamming distance. So these are the actually the mathematics that is behind, and these are the distance metrics which are the backbone of even clustering. Other than these things, even we have Goward distance, cosine similarity, Jaccard are also there, but I've just only listed very few distance metrics, which is frequently used by default in many of the clustering techniques today. And these are the backbone of the clustering algorithms that is available at present. And we know that why we need to go for clustering and what are the applications at present, like anomaly detections can be done, and even image segmentations, medical imaging, so like social networking analysis, all those things. No, we need to, there are the practical applications or the uses of clustering. Okay, so large data sets can be actually simplified in terms of by applying clustering. So these are the distance metrics that are the backbone of clustering. So let me just to give you an overview of what is Euclidean distance, Manhattan, all these things. So Euclidean distance, actually, you will be finding the square root of sum of squares of differences between the corresponding elements. So given the two vectors, from two vectors, you can find out the Euclidean distance, and the formula I've just given in the included in your slide. You can visualize it. For n dimensional, it is generalized. Okay, same way for Manhattan, it is actually the absolute differences. Some of the absolute differences between the points across all the dimensions is Manhattan distance, and this is the one is given here is the two-dimensional space, and for n dimensional, it is generalized here. And Minkowski distance, it is actually generalized form of Euclidean as well as Manhattan, because we'll be just using the square root. Their sum is there, but we'll be finding the difference. It is absolute difference of the points. So see, the things like Manhattan or Minkowski or Euclidean, no, whenever there are numerical data, we will be just applying all those things. What about when we have or prefer to use categorical values? So whenever we have categorical values, the one which is best suitable is Hamming distances. So here, the Hamming distance, just for an example, I took two strings over there of same length. So we will be just finding the best match over that. So here, the length of the string is equal. Okay, then only you can apply the Hamming distance. So according to this particular two strings, 7 characters, actually, the first 7 characters, EUCLIDE and Manhat. Okay, the 7 differences are there. 2 characters are similar. So you can find the Hamming distance here. It will be just recommending, or we identified that as 7. Okay, so note that the larger the Hamming distance between two strings, more dissimilar those strings will be. So always our aim is to find the similarity. Okay, so whenever it is larger, it is dissimilarity is more. That is how we have to conclude it. So before moving on to the clustering techniques, let me just share my screen where in my there is the distance metrics in Google Colab. I've just executed it for your reference. See here, see, we have to import the distance package for calculating Euclidean distance. That is the Manhattan distance. It is available inside the distance package with the name of city block. And we have Minkowski, as the name itself suggests you. It was defined in the same name. Hamming is the method name that is available in the distance package. So we have to just import that. For explanation purpose, I've just declared 2 points over here. It was printed here. And the Euclidean distance is being calculated just by calling the Euclidean method and pausing the 2 points. So you will be getting the Euclidean distance for printed for your reference. It is 5.19. Same way, Manhattan distance, the city block is the function that is available inside your distance package. So you have to just pass the 2 points from which you want to find the Manhattan distance. And it was printed, and we got the answer as 9 over here. Using Minkowski, actually the distance between the 2 points and the method, actually it was clear. It is Minkowski itself, which is under the distance package. And the distance here we got is 4.326. When we are just moving towards Hamming distance, according to the same example which I have included in the slide, I've just passed those 2 things, and we got here it is 7. So depending upon the distance, okay, distance metrics, you can just choose the, you can create the clusters. So I just wanted to share this, what are the suitable methods and in which package you have that. And moving on to the presentation part. So this is actually the math behind the clustering techniques. It is few more, but I would like to focus the various clustering techniques that is available. And there are around 10 clustering techniques. I'm just going to share the coding part of it, how to execute with sample data, and what are the hyperparameters that is there for each and every method we are going to discuss now. Okay, and a special mention thanks I have to provide for Jason Brownlee, who is actually a professional developer and machine learning practitioner, because I've sourced all these content from, that is the explanation of the clustering techniques from that. Okay, so we'll now move on to all these things. We are going to discuss one by one. So let me just share my screen. Clustering techniques. So to start with the clustering techniques, the first one which I have mentioned is affinity propagation. So one by one we will discuss. So it is affinity propagation. So before using that, I've just created a sample data set here. See, this particular sample data set is called as synthetic data set, because it is not actually a real data set. Rather, it is a computer program generated one. So whenever we are learning something or test, if you would like to explore something with the particular available algorithms, we will have to create our own data sets. So these are all actually, see, the make classification method. With the help of that, we have created a synthetic data set of 1,000 samples, and with the 2 input features, 1 cluster per class is being specified over here. Okay, and this is how we have classified here. And by default here, it is applied multivariate Gaussian algorithm is being applied over here. Okay, so this is just we have created a synthetic data set, and I'm just going to explore all the 10 techniques or 10 algorithms we are going to use for this particular sample size of 1,000. Okay, so moving on to the affinity propagation clustering. See, before I've just explained, I'm going to now use only Google Colab today. You can even install, and we are all aware that we can install it. And the basic thing is we need here SCI kit, and that is learn. That particular thing we have to include or install. So we know the procedure to install, pip install, and SCI kit learn package you have to install. And once installed, you can check the version by specifying sklearn.version. That is, you will have __ version __. That is the method that is used to check the version. So once it was installed, you can work. Otherwise, nowadays it is very easy to work with Google Colab itself. So I've just uploaded everything here, and it is available in the Google Colab itself. So affinity propagation clustering. So what is this one? Like, see, many of the clustering algorithms actually, we need to specify the number of clusters we need. So see, for example, I'm just going to have a data set of 1,000 items. I would like to create some number of clusters. Some of the algorithms, no, we will be specifying the number of clusters required. So I want to create them or group them with 2 clusters or the n number of clusters. Like that, we used to specify. But this affinity propagation algorithms, there is no need to specify the number of clusters at all. So you can have a glance here. Affinity propagation is being called with 2 other parameters. Actually, this particular algorithm or the technique, it creates clusters by sending messages between data points until convergence arises. So we'll be sending messages between the data points until convergence occurs. Since we are not actually specifying the number of clusters, 2 important parameters that is required. One is the preference and the other one is the damping factor. So these are the important hyperparameters that is to be tuned to improvise the accuracy of our results. So affinity propagation, the preference actually, it controls how many prototypes are used. The alternate terms that we'll be using is exemplars, like it controls how many prototypes are being used as the preference. And the damping factor actually, it damps the responsibility and availability of the messages to avoid the numerical oscillations when updating these messages. So exemplars are members of input set that are representations of the clusters, like message sent between pairs of a pair of the points, right? That is suitable of one particular sample to be the prototype for the other. So which is updated in response to the values from other pairs. So this updating actually happens iteratively until the convergence occurs. As I was telling you that it clears clusters by sending messages between data points until convergence. That is, responsibility and availability matrices will be created. And iteratively it was done because clustering mechanism is actually an iterative mechanism. So this updating happens iteratively until convergence occurs. So the final exemplars, that is the prototypes, are actually chosen and they'll be declared as the final clusters. So to just work out that affinity propagation, the preference have just given us -50. The damping should be like 0.5 to 1. So you can just tune your according to your data set, you can in a trial and error method, you can just change these parameters, but the damping factor should be like 0.5 to 1. Keep that in mind. And just a plot is being given here. See, this is the output I'm able to get to the data set, that is a synthetic data set which we have passed here. And see, when we just look at the output of this, it is not being clustered, right? So we are not actually able to get good results because we know that there are plenty of clustering techniques and algorithms that is available. Okay, we cannot just like that tell that this particular algorithm suits for this data, or we can just conclude it by applying our data set to the existing algorithms, and by looking at the what is the result you are getting, you can just select the best one according to our application. So according to the data set that we have used here, we are not able to find a good result over here. See, look at the graph here. There is no cluster at all. In all colors represents, it is not creating the best grouping. Okay, according to this particular data set that we have passed here, affinity propagation does not actually, I'm not able to get good results for my data set which I have passed. Okay, so we will now proceed with the next technique, which is nothing but agglomerative clustering. Okay, so agglomerative clustering actually, we will be actually creating some dendrographs. Okay, so it involves merging examples of the data sets until the desired number of clusters is achieved. So we will be actually beginning with every point in our data set as a cluster. So we will be starting with the each and every data item, that is data points. Okay, every point is initially considered as one cluster. So what we have to do is we have to find 2 closest points and combine them into a cluster. Then again we find the next closest point and those become a cluster. So we have to repeat until desired number of clusters is achieved. Suppose you want to cluster the entire data in only one group, you have to stop and you have to provide the number of clusters parameter as 1, and you have to proceed. Okay. Suppose if you need the number of that is, you have to repeat it until the desired number of clusters is achieved. So let us now explore how this particular agglomerative, that is the agglomerative clustering, applies for our data set, that is the synthetic data set that we have passed. So here, as I told that, we have to tune the parameter, which is a hyperparameter that is to be tuned is this n clusters, number of clusters. We have just given us 2 now. So let us now look at the output of it. So this is what the output of the particular agglomerative clustering concept. So reasonable actually compared to the previous one, for the synthetic data set that we have passed over here, we are able to get some reasonable grouping, right? See, look at the previous output which we got compared to this. Okay, this is actually the data, it is not at all clustered according to my data set. Okay, it is not good result. Whereas here to a somewhat reasonable grouping is found over here. Okay, so what we have to do is generally we have to pre-process the data. Even the output of the clustering can be used as a pre-processing stage for some other machine learning algorithms also. Okay, so agglomerative clustering, actually here we are able to find out some reasonable grouping is being founded. Okay, so next one we will be just discussing is breach. Okay, so breach, it is actually balanced iterative reducing in clustering using hierarchies. So as the name itself suggests that it involves constructing a tree structure from which cluster centroids are extracted. Okay, so breach algorithm actually we'll be constructing a tree structure. Okay, so from that particular tree structure, centroids are extracted, and this is achieved with the help of breach class only. So we have to import that. It is available in sklearn.cluster package. So we have to import the breach package over here, the class to be imported. And here, see, look at the hyperparameters that is to be tuned is the threshold and the number of clusters. To tune the threshold and the number of clusters are the hyperparameters. And let us now have a glance on how the output will be when we are applying this particular algorithm for our synthetic data set. Okay, see, now look at the output here. See, compared to the previous two algorithms that is being applied to our synthetic data set, we are able to achieve some excellent grouping is found. It was we are able to just cluster them into 2 different groups because we have specified as the number of clusters required as 2. So we are able to get an excellent grouping is being found in case of bridge algorithm. Okay, so moving on to the next one, it is DB scan. So density based spatial clustering of applications with noise. So density based spatial clustering. Okay, in short, we can call like that. It is DB scan, and DB scan actually finds the high density areas in the domain. See, when we are providing the data set, whatever data set we are trying to provide, so it will just create clusters in terms of finding high density areas in the given domain. So expanding those areas of the feature space around them as clusters will be done. So first it will just identify the high density areas in the domain, and then expanding those areas of the feature space around them as clusters. Okay, that is the basics of DB scan. And as usual, in order to use that for your data set, we need to import this particular DB scan, okay, class from the sklearn.cluster. So the prerequisite is SCI kit learn. Okay, that is SCI kit library has to be installed. Okay, so from that you will have to import this particular DB scan class. Okay, and I'm just calling the DB scan class. And when you explore or look at this, see whatever parameters we have given here, just particularly I have used only the hyperparameters. Okay, so we are all aware that what is the difference between the parameter and hyperparameter. Okay, so hyperparameters always will create an impact in the prediction or clustering, whatever it is, the end result. When you tune the learning rate, Sometimes even the epoch count in particular algorithms, no, we will be having a great fluctuations happening in my result. So we have to tune them according to our pre-processed data set. Which particular hyperparameter tuning will yield greater accuracy, it was we have to find out. Okay, so I have just given here, these are the two hyperparameters to be tuned, EPS and mean samples. Apart from this, we have even other parameters also, but for discussion purpose, I've just included only the hyperparameters to be tuned. So DB scan, we are just applying to the existing data set, and we are able to get the output like this. So this is actually the output of DB scan. And see, when you just have a glance over here, it was somehow reasonable, but it is not that much good or excellent when compared to bridge. It is not that bridge is far better than DB scan. Okay, we cannot conclude like that. For this particular data set, it is applying or it is responding like that. So I'm just selecting which one is the best according to our requirement. Okay, so DB scan actually is producing an cluster like this. So this is somehow compared to the affinity propagation algorithms and all, this is reasonable group is found. Okay, so what we have to do is we need to tune them. So you have to just tune the min samples, EPS values, always in a trial and error method. You can just check, see, for EPS value as 0.30 and min samples as 9, we are getting this as the output. Okay, so you can just like that check it, like when we are increasing it to some 45, what is the output we are getting. So the hyperparameters, see, let me just have a try like that. Whatever hyperparameters that is being specified according to the expectation, we have to try. If there's no change, that is the saturation state. Okay, so let us now watch. It is being changed to 0.45, 0.45. Whether any changes is there in the output. Let us just wait. See, even it was 0.30 itself, it is okay. Okay, but now it has been clustered everything as one single group. So what will happen when we are reducing this? Like that, no, hyperparameters always, we have to change the values, and see, when it was 30, it is reasonable somewhat. So let me just check it with 20. See here, there is no that much difference, a slight difference over there here. Earlier for 30, we didn't get that. Okay, these number of blue clusters, like this data items, this group is not there. So like this, always we have to tuning of hyperparameters is the magic actually. Okay, because Python actually nowadays is helping us a lot. And even sometimes, no, when we are just like the calling the algorithm, okay, it is like a black box. How we are getting the accurate answers is hidden from us. But tuning the hyperparameters or identifying actually which particular parameter is hyperparameter, and when we change them, our output is getting changed at, is actually a great thing. So DB scan. So this are the hyperparameters. So when we change it here, we are actually, it is showing a great impact in the output of clusters. Okay. So we'll now move on to k-means clustering algorithm. So k-means clustering algorithm, it is actually, we are all familiar with that k-means. So most widely and commonly used clustering concept is k-means. And to use this k-means, actually we should import k-means. Okay, k-means over here, and then you have to use the class over here, and the particular number of clusters that is required is 2. I've just specified as 2 here. And using that K means we are able to get the output like this for our data set. Okay, that is a synthetic data set, whatever I'm using here. Okay, 1 minute. Let me even open another notebook. I don't know why I'm not able to open this. Let me close one of the tab. File. So here, actually, using again a synthetic data set, like instead of using make classification, just use the make blobs over here. And this is actually the available one. And for this, I've just applied k-means over here. And with the number of clusters required as 4, this is how it is. I'm just getting an output here for this particular data. I just wanted to show that. And even the same thing for agglomerative clustering, the number of clusters I've suggested here is 4 agglomerative. And we know that it's a bottom-up approach actually. It combines like look at this one. It is all the points here, because already we have completed that. I thought of showing this. See, every individual point, actually the data items, items or data points are actually clusters. So it will be just combining them into a cluster. Okay, so we find the next closest point and those become the next cluster. Like that, no, we are repeating to get the number of clusters. Okay, so this is how the output of the agglomerative for this data set or synthetic data set that is being created. And see, you can even find out the number of clusters, how many clusters you need. Like you can pass a data set and you can identify the number of clusters required. See, whenever you have the by applying this elbow method, see, you have this sharp bend over here. So the suggested number of clusters for our data set is that is required is number 4 according to this example. So like this also you can find out the number of clusters before, just like that in a trial and error, providing the number of clusters as 4, you can get it. So here we'll now move on to the next one. K means following that, it is mini batch K means clustering. Okay, so this mini batch K means clustering actually is a modified K means. Okay, we can call like that. Mini batch K means clustering is actually a modified K means algorithm. So it makes the updates to the cluster centroids actually using mini batches of samples rather than entire data set actually. Okay, so the improvisation that is being given to K means, existing K means, is it will be just using some small samples. Okay, so that is the name suggested as mini batches. So using the mini batches of samples rather than the entire data set, it actually updates the cluster centroids. So we know that like huge data sets will be having, like for example, I can provide some, I'm expecting some 4 centroids, and clustering is an iterative process. The centroids will be keep on moving, right? So if it is saturated, if it is not changed, we'll be stopping the iterations. So here, mini batches, instead of just the entire data set, mini batches of the samples are used here to just update the cluster centroids. That is the difference when compared to k-means. So this actually, it is faster, okay, for larger data sets compared to k-means, this one is faster. And to just use it in our data set, there is a synthetic data set that we have already created. We need to import this instead of k-means, this mini batch k-means. Okay, you have to import that, and the main configurations for tuning is this n clusters parameters. Okay, so the mini batch k-means is the package or the class that we have to use it in the package. And we need to tune the hyperparameter, that is the number of clusters. So let us have a look on what is the output of mini batch k-means. Okay, so we'll move back to the output of k-means here. See, this is the output we got for our data set by applying k-means. And when we are now trying with this mini batch k-means, see, actually, the algorithm wise, they are similar, but to update the cluster centroids, okay, rather than using the entire data set, the mini batches will be used. That is a small samples. Okay, as mini batches of samples is used. That is the difference, because we need to achieve fast, there is speed. Okay, so this makes actually faster for larger data sets. So we are not having that much difference in the internal processing. Okay, so it is same as the k-means. Are you able to compare, like what is the difference? Okay, the result is similar, okay, to k-means. Okay, so then moving on to the next one, it is mean shift clustering. Mean shift clustering. See here, we will be actually if there is it involves in finding and adapting the centroids. Actually, how we'll be finding and adapting the centroids, no, from the given data set? It is based on the density. Okay, so it is based upon the density of the data items. Okay, so it is actually the density examples in the feature space, I can put in this way. So it involves, there is a mean shift clustering algorithms actually involves finding and adapting centroids based on the density of the examples in the feature space. Okay, so to use that, actually the class recommended and it is available in the packages mean shift itself, and we have to just use them here. And see here, I have not just passed any of the parameters over here. Sometimes even you can, that is the mean shift by default, what is the output it is producing. Okay, so just have a glance over here. It is actually a reasonable set of clusters are found in the data. Okay, comparatively to the initial one, like the first algorithm that we discussed, right? So compared to that, here we are able to get the reasonable setup, that is comparing to the affinity propagation algorithm. Some reasonable set of clusters are found, but it is not that much efficient compared to breach, which we come across earlier. Okay, so moving on to the optics clustering. Okay, so optics clustering, actually how this works. Okay, ordering the points to identify the clustering structures. Okay, that is actually the expansion for optics. We are trying to order the points to identify the clustering structures. So see, this optics clustering actually is modified version of DB scan. Okay, so earlier we discussed an algorithm called a DB scan, that is density based spatial clustering, right? So this one, okay, so optics is actually modified version of DB scan. So here to use that, actually for our model, okay, we have to import optics class and the parameters, because it is similar. Okay, but it's just a modified version here. Okay, so modified version of DB scan. The parameters that is being tuned here, that is the main configuration to tune here is EPS and min samples. Okay, so when I just give here, instead of, that is in DB scan, we tried with the 0.30, that is 0.30 and 0.2025, and we found what are the impact of the hyperparameters to get the accuracy, the clustering. Okay, so here in optics, I'm just using here, it is 0.8 now. So in the mean samples 10. So look at the output here. So the output actually is not recommended to use. That's based on the output. Okay, we are not supposed to use this particular optics algorithm for our data set. Okay, I have just tried it with some other, that is by changing the hyperparameters also. So it is not actually suitable for this data set because we are not able to achieve the reasonable result. Okay, so even DB scan actually I'm able to get, because see, that is why we don't have any hard and soft rules like this particular algorithm is suitable for this particular data set. Okay, so it all depends upon the tuning of the main configurations, that is the hyperparameters, and we need to actually identify the hyperparameters. Okay, that is required and to be tuned. And we'll now move on to the spectral clustering method. Okay, so this particular spectral clustering is a general class of clustering method. Okay, and this is drawn from linear algebra. So spectral clustering method actually is a general class actually of, it is one of the category of clustering methods. And the basics of spectral, that is your spectral clustering, is it is drawn from linear algebra. And to use that, we have to import spectral clustering as the class, and the parameters that need to be tuned over here is the number of clusters, n clusters. Okay, so this actually gives an impact. Okay, so to specify the estimated number of clusters, okay, what is the estimated number of clusters that is required in our data set? Okay, so we have to specify that n clusters is the main configuration that needs to be tuned. Okay, so we can suggest, or we can just use this as the hyperparameter for spectral clustering. And when we apply that spectral clustering with n clusters as 2, so this is what the output we are getting. And this one actually is reasonable clusters were found. Okay, so this is reasonable compared to the previous one which we explored just now. Okay, so this is spectral clustering. And moving on to the next one, it is the Gaussian mixture. Okay, so Gaussian mixture summarizes actually a multivariate probability density function with a mixture of Gaussian probability distributions. Okay, we are all aware about that. And to use that, we have to import the class named as Gaussian mixture, and we need to use it with the particular hyperparameter that needs to be tuned is n components. So the number of components, usually we used to have like n clusters, number of clusters, but that was given here, and then the name n components, that is not number of components. So number of, this is actually the number of clusters that is estimated. Okay, to specify the estimated number of clusters here, n components is 2 I've given. So let us now view the output of it. See, it was actually identified perfectly. Okay, so I think by now you are aware that, see, we have just explored. See, we know that the clustering technique is a very vast area. Like within 1 hour, exploring each and everything, like k-means itself can be conveyed, or it consumes like 1 hour. We can discuss with different data sets to explore a lot. But what I planned is like what are the overview of what are the available clustering techniques that is available there, and what is the hyperparameter that need to be concentrated when using the particular technique is the focus of discussion today. So the spectral clustering, so we have discussed almost some 10 techniques over there, which I've listed in my PPT. Okay, so you can even conclude, or you inferred that, and we found, okay, see, through the synthetic data set of 10 samples that we have created, Gaussian mixture clustering, actually, we are getting a perfectly, it was identified, right? The clusters were identified perfectly. And this is okay, reasonably, it was good, but comparatively, for our data set, Gaussian mixture best suits. And this one, breach. Okay, that is balanced iterative reducing and clustering hierarchies. Okay, so this algorithm actually is good, but comparatively, see here, we are not that much able to have the clusters, but this is also excellent. So this one is the last one that we discussed now, which is perfectly classifying them. Okay. So like this, we have to actually, in trial and error, we have to try. And I just thought of giving you an overview of all the available clustering techniques and the distance measures which we discussed previously, like the math behind the clustering techniques. Why it is very important is because the distance metrics, no, it is common for all the supervised as well as unsupervised mechanisms also. Like we know that the distance measure should not be negative. Okay. And our clustering actually will help us to discover the patterns, and it helps us to in the knowledge discovery. And one more thing I would like to tell. So see, when we are actually creating the clusters, no, based upon the similarity between the items. Okay. So here, for example, to find the similar books by the author name, like that, no, we'll be having some features. How to find that similarity between two items practically given a data set, like it is defined by some features, right? So for example, similar books by an author. So like that, no, so now author is one of the feature we are having. But when the number of features increases, it creates actually a complexity to create the clusters actually. So depending upon the data set, we have to choose the suitable clustering. Okay. So this is what I have prepared. And these are the references which I took. And as I mentioned earlier, I have just referred all the 10 algorithms for machine learning mastery. And so Jason Brownlee actually is a person, okay, who is working with the he is actually a machine learning practitioner, and he helps the developers. Okay, so from there I just referred all these things, and these are some of the references points, and that is from my end. So last 10 minutes, any queries? If there, you can raise so that if I'm able to, I can.
Thank you, ma'am.
Ma'am, good morning.
Good morning, ma'am.
Your presentation is excellent.
Thank you,
I need one clarification. What kind of distance measure is preferable for Birch algorithm? You told that Birch is best suited for some of the data set. I need
the
to know
data set
what,
which I have used, madam, for my
okay. I need to know what kind of distance measure is applied for this Birch algorithm.
Ma'am, among the variable, yes, ma'am.
You have mentioned some of the distance measure, Manhattan and
yes, ma'am. Euclidean,
etc. Euclidean, which is best for this Birch algorithm. Or you have
yes, ma'am.
Are you applied? Which one you preferred for this data set?
Ma'am, actually, I have not, see, when you just look at my code, I have not explicitly specified any of the distance metrics over here. Okay, because when I just call that particular bridge itself, it is invoking or applying by default the distance metrics. So from my viewpoint, actually many of the algorithms applies Euclidean distance, ma'am, compared to the available things. Euclidean distance is best suitable because Hamming code and all is for categorical data.
Okay.
So Euclidean distance best suits for even the k-means, all those things.
Okay.
The Gaussian there is a Gaussian algorithm also uses
Okay.
this one, that Euclidean distance, ma'am.
Okay, ma'am.
So up to
Okay.
my prediction, I'm not that much aware whether Euclidean distance is being applied. I've just tested with all the different algorithms as one synthetic data, but it was actually given in all the
Okay.
statements the best one distance median is most probably used by many of the clustering algorithms. If we
Okay.
want, we
Suppose.
explicitly can define. We can define
Uh,
and we can invoke it in our code also, ma'am. We can define the Euclidean distance measure, or if you want to change it, we can just define it in
okay.
our
Suppose,
code and
madam.
we can include them. Yes, ma'am.
Suppose I want to alter the distance measure. Is it possible in that algorithm?
That is what I'm
Suppose
telling, ma'am. I have come across certain codes from the GitHub and all those things. They are defining their own distance metrics according to their applications, and that code can be integrated over here with certain modifications. Like we have to, the existing class cannot be changed, right? For example, if I'm calling the breach method, we will not be able to change that. Rather, what I can do from my end is I can revise, and as a researcher, we will be revising some algorithms, no ma'am. So same way we can create our own modified version of breach where this particular distance metrics can be used to improvise the result. Like that we can, but we are not supposed to make the changes in the existing class, right? It
Oh,
was built in
okay,
already.
madam.
We can develop our own algorithms like modified breach algorithm. The default one,
Okay.
it is being used to this distance metric. So it is preferable, and this metric is suitable for the our data set or application. We are opting this. Like that we can do, ma'am. But existing packages and all, we will not be able to change it.
Okay, madam. Thank you. Thank you so much, ma'am.
Thank you, madam. Thank you, ma'am.
Participants, any other queries are there? Thank you, Nalini ma'am. Thank you for a wonderful session. And this is the time for the vote of thanks. I would like to thank Dr. S. Nalini, Associate Professor, Information Technology of Rajalakshmi Engineering College, for giving a very crystal clear crystal clear about the clustering techniques. And I would also like to thank the management of Mount Lebanon Agro Engineering College for allowing us to conduct such an FDP. And I thank all the participants for your participation. And I would request all the participants to fill the feedback form with the faculty ID given to them. Nalini ma'am, thank you. Thank you so much, Nalini ma'am.
Thank you. Thank you, madam. Once again, I'm thanking the management, and special thanks to Mrs. Deepa, madam, for inviting me as a speaker of your 5 days FDP. And I'm feeling very proud to be in the part of the second day. Thank you so much, madam.
Ma'am, it's our proud, ma'am. Thank you, ma'am.
Thank you.
Participants are requested to fill the feedback form within 30 minutes. Thank you. Thank you all. We'll end up the session. Clustering technique.